This next chapter is all about how energy is related to chemical reactions. And so in this video, we're going to talk mostly about concepts relating to energy and how that relates to chemical reactions. So let's start with some definitions. The study of relationship between chemistry and energy is called thermochemistry, and this is a branch of thermodynamics. Now, when we say energy, I think everybody has a general idea of what that is, but I think it's helpful to have a more specific definition. So energy is the quantitative property that must be transferred to an object in order to do work on it or to heat it. Another way you hear energy defined sometimes is energy is the ability to do work or to transfer heat. And so work is a force acting over distance, right? So somebody pushing this block is doing work on it. And heat is the flow of energy caused by a temperature difference. So when you have this red hot coil, that is at a much higher temperature than this pot of water, and so the heat is being transferred from the coil to the water. And so the energy is being transferred as heat. So energy is something that an object possesses, and the way we transfer energy is through either heat or work. Another way that we often classify energy is by classifying it as either kinetic or potential energy. So kinetic energy is the energy due to motion, and potential energy is the energy of position or composition. And sometimes it's referred to as stored energy. A physicist might yell at me for using that definition, but I think it can still be kind of helpful when we're thinking about what potential energy is. And so chemical energy is a type of potential energy. And so this is the energy associated with the positions of the electrons and the nuclei. And so in some sense, chemical energy is the energy that's stored in chemical bonds. And so just two other examples of potential and kinetic energy. When this archer pulls back on the string of the bow, right, that energy is in some sense stored, or more correctly, right, it's due to the stretching of the spring and the bow that is giving it its potential energy. And then when she releases the string, right, that potential energy is transformed into kinetic energy, the movement of that arrow. Right? Another way we can have potential energy is when the ball is off the ground, right? So its energy of position or stored energy as that ball is lifted up off the ground, when she releases it, that potential energy gets converted into kinetic energy as the ball starts moving under the force of gravity. So already in this class, we've talked about the law of conservation of mass, or the law of conservation of matter, and that is that matter cannot be created or destroyed. The law of conservation of energy is that energy can't be created or destroyed, but it can be converted from one form into another. Another way to say that is that the total amount of energy in the universe is a constant. Sometimes you'll also hear this referred to as the first law of thermodynamics. And so just an example of the law of conservation of energy and energy being converted from one form into another, we talked on the previous slide about one form of potential energy is chemical energy. And so it's the energy stored in chemical bonds. Well, it turns out there's quite a bit of energy stored in the bonds of gasoline, of the molecules that make up gasoline. And when we burn it, the gasoline is converted primarily into carbon dioxide and water, and there's much less energy in those bonds. And so that energy is released by that chemical reaction when we burn it. We convert the gasoline into carbon dioxide and water. And so that energy is primarily released as heat that we can use to expand the air inside the pistons in our automobiles, assuming we have a standard combustion engine. And so that chemical energy that was stored in the gasoline molecules gets converted into the kinetic energy of the pistons moving inside your engine, which then gets converted into the kinetic energy of the turning of the tires, and it allows your car to be propelled forward. And so that energy that was stored in the chemical bonds is converted ultimately into the energy of your moving car. So it's also good to talk about how temperature is related to energy. So thermal energy is a type of kinetic energy associated with the random motion of atoms and molecules. So atoms and molecules are not static things. They are constantly moving around. They are constantly vibrating. They are constantly rotating. And as we increase the thermal energy of a sample, the atoms and molecules vibrate more. They rotate more. They move faster. And so the more thermal energy they have, the faster those atoms and molecules are moving. And temperature is a quantitative measure of the average thermal energy in a sample. And so fast-moving molecules have high thermal energy, and we might qualitatively describe that as hot, whereas slow-moving molecules have low thermal energy, and we would refer to them qualitatively as being cold. And so, when the temperature, say, in your house increases, right, what's happening is that the air molecules in your house are moving faster than they were at the lower temperature. So, all right, so we've already talked a little bit about heat, and this is the transfer of energy, but it's good to talk about it since we've also talking just now about temperature. So heat is a transfer of energy between two bodies at different temperatures. And so heat always travels from hot objects to cold objects, right? It will not spontaneously go from cold objects to hot objects. That's actually another one of our laws of thermodynamics, but we'll talk about that more specifically next semester. And so if we have two samples at different temperatures and we bring those together, the excess thermal energy in the hot sample will be transferred to the cold sample until the two temperatures of the two samples are the same. At that point, it's said that we've reached thermal equilibrium. And so this will always happen. Heat will always be transferred from a hotter object to a colder object until those objects have the same temperature. So when we talk about chemical reactions and energy, in general, chemical reactions or physical processes can either give off heat or absorb heat from their surroundings. And so we have names for these processes. A chemical change that releases heat is called an exothermic process. And so we've used the example of combustion a couple times. Right? Combustion is an example of an exothermic process. Right? As outsiders to the reaction, right, a combustion reaction feels hot to us because that chemical reaction is giving off heat, which we're then absorbing. A chemical change that absorbs heat is called an endothermic process. And so if you've ever used any of the instant cold packs, right, usually you kind of smack the bag and then the bag gets cold. Well, there's an endothermic reaction going on inside the material of that instant cold pack. And it feels cold to us because that is an endothermic process, and so the chemical reaction is absorbing heat from our bodies. So let's talk units and energy. So there are a lot of different units that we can use for energy. Two of the most common are calories and joules. And so calories is the one that was used more commonly historically. And a calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius, or 1 Kelvin. And you often see calories still used, for example, in nutrition. And in nutrition, often when they give the calories in a food item, they're actually giving calories with a capital C, and these are actually kilocalories. A calorie with a capital C is 1,000 calories with a lowercase c. So it can be a little bit confusing, but if you're dealing with nutrition, you're probably dealing with calories with a capital C. And so to a chemist, we would call that a kilocalorie or a kcal. Now the SI unit of heat, or the SI unit of heat, work, and energy, and that we'll be using most commonly in both 1211 and 1212 is the joule. And so the joule is named after chemist and brewer James Joule, and he's one of the scientists that's given credit for the law of conservation of energy. And the conversion factor between calories and joules is given down here. 1 calorie is 4.184 joules. Now, when we talk units, some things I think we have a decent idea of what they are. Right? We kind of have a general idea of what a gram is when we're dealing with mass, or you've dealt with milliliters before this class, and so you had an idea of what that is, but you might not have thought a lot about the energy of joules and calories. And so if we go to the next slide here, right, just to give you an idea of how big a joule is, so one explanation that physicists like to use is a joule is the energy required to raise a small apple 1 meter off the ground, right? And that the reason people like that is they're thinking Isaac Newton, right, and the apple falling on his head, and that's how the story goes. The idea for gravity. To give another example, so 1 gallon of gasoline contains about 130,000 joules. I'm sorry, not 130,000, 130 million joules. Or another one that physicists like is a jelly donut. So a jelly donut contains about 1 million joules. And so that's quite a bit, right? A jelly donut is not that far off from the energy contained in a gallon of gasoline. So this is why we want to limit our intake of jelly donuts. A lot of excess energy there.